Welcome, everyone. Today, we are diving into a critical aspect of machine learning operations, or MLOps, configuring identity and access management for your Azure Machine Learning workspaces. Let's get started. Welcome to our first module. What exactly is Identity and Access Management, or IAM, in the context of an Azure Machine Learning workspace? In simple terms, it is the fundamental security layer that dictates who can enter your workspace and what actions they can perform once inside. We break this down into two basics: authentication, which proves your identity via Microsoft Entra ID, and authorization, which uses Azure RBC to check your permissions. Why do we care so much? Because in an enterprise environment, your ML workspaces house highly sensitive data, intellectual property in the form of models, and expensive compute resources. By tightly controlling access, we prevent both accidental misconfigurations and malicious data breaches. We achieve this by fully integrating our ML workspace with Microsoft Entra ID, ensuring a seamless, scalable, and centrally managed security posture. Take a look at this high-level flowchart. It illustrates the journey of a request. When a user or an automated application attempts to access the ML workspace, they must first authenticate against Microsoft Entra ID. Once their identity is proven, the system checks Azure RBAC, the authorization gatekeeper. If they have the correct role assignments, they are granted access to the workspace. If not, they are immediately blocked at the perimeter. This is your first line of defense. Let's move on to the basics of who we are managing. In Azure, any entity requesting access is called a security principal. This could be a human user, but managing individual users does not scale. Instead, we use security groups. You group your data scientists together, your ML engineers together, and you assign permissions to the group. Why is this important? It aligns perfectly with the Zero Trust security strategy. Zero Trust teaches us to verify explicitly, assign only the least privilege necessary for a job, and always assume breach. By using meticulously managed groups inside Microsoft Entra ID, we ensure that if an account is compromised, the blast radius is strictly contained to the permissions of that specific group. Furthermore, Entra ID logically isolates your entire directory into secure tenant containers, preventing any cross-contamination of access. This mind map breaks down the core tenets of the Zero Trust model as applied to IAM. In the top right, verify explicitly reminds us to always check identity and context. On the right, least privilege highlights the importance of assigning minimal access via role-based access control and security groups. Finally, assume breach focuses on designing our architecture with tenant isolation so that if an attacker gets in, they are trapped in a highly restricted container. Keeping these pillars in mind is essential for secure ML operations. Now, let's explore exactly how we grant these permissions using Azure Role-Based Access Control, or RBAC. Azure RBC is the engine that drives authorization. It allows you to segregate duties within your team. Instead of giving everyone unrestricted administrative rights, you assign specific roles. There are three fundamental built-in roles: the owner, who has full control including the ability to grant access to others; the contributor, who can create and manage ML resources but cannot modify access rights; and the reader, who can only view existing resources. You map these roles to users or groups at a specific scope, like your entire subscription or just a single ML workspace. But what if those built-in roles are too broad? That is when you create custom roles. Custom roles allow you to get incredibly granular, for example, granting a data scientist the ability to submit an automated ML run, but explicitly denying them the ability to delete a registered production model. This diagram illustrates the anatomy of an RBC role assignment. It consists of three parts. First, the security principal, the who. Second, the role definition, the what they can do, like contributor or reader. Third, the scope, the where they can do it. Notice the scope hierarchy at the bottom. You can assign a role at the broad subscription level, narrow it down to a resource group, or lock it down tightly to a single, specific ML workspace. Narrow scoping is a best practice for ML security. Let us take a deep dive into non-human identities, starting with the service principal. A service principal is essentially a user account for an application or a script. In modern ML environments, we rely heavily on machine learning operations, or MLOps, to automate our workflows. You absolutely should not use a human data scientist's credentials to run an automated CI/CD pipeline. It is a massive security risk. Instead, you create a service principal specifically for your automation tool like GitHub Actions. You assign this service principal an RBC role, perhaps machine learning contributor, restricted solely to the workspace where the automation runs. The credentials for this service principal are then stored securely in a vault, such as GitHub secrets. When your pipeline executes, it uses these secure credentials to log into Azure and trigger your ML training jobs, ensuring a secure, headless, and fully automated deployment process. This sequence diagram shows the automated MLOps authentication flow. On the left, our GitHub Actions starts the workflow. It first fetches the securely stored service principal credentials from GitHub secrets. It then passes these credentials to Microsoft Entra ID to authenticate. Entra ID validates the service principal and returns a secure access token. Finally, the GitHub action uses this token to communicate with the Azure ML workspace and submit the training job. No human intervention, no exposed passwords. Our second deep dive explores an even more secure paradigm, managed identities. While service principals are great for external tools like GitHub, what about Azure resources talking to other Azure resources? Enter the managed identity. Managed identities provide a completely keyless authentication experience. This means no passwords, no secrets to store, and nothing to accidentally leak in your code. How does it work? Let's say you have an Azure ML compute cluster that needs to pull training data from Azure Blob Storage. Instead of embedding a storage access key in your Python script, you enable a managed identity on the compute cluster. Microsoft Entra ID automatically manages this identity behind the scenes. You then use Azure RBC to grant this specific managed identity, storage blob data reader, access. The compute cluster can now pull the data securely, and you never had to touch a single password. This is the gold standard for intra-Azure security. Look at this flowchart to see the elegance of managed identities. Our Azure ML compute cluster on the left inherently possesses a system-assigned managed identity. When it needs data, it simply asks Microsoft Entra ID for a token no passwords required. Armed with this token, the compute cluster requests data from Azure Blob Storage. Storage checks the token against Azure RBC rules. Because we explicitly granted the identity access, the data flows securely. It is seamless and highly secure. Now that we understand RBC, service principals, and managed identities, how do we apply them to a real enterprise architecture? The key is environment isolation. When deploying models at scale, you never train and deploy in a single workspace. Instead, you create separate, physically and logically isolated Azure ML workspaces for development, staging, and production. Why? Because we must protect the production environment to ensure a stable experience for the end users. Here is where IAM truly shines. By applying RBAC at the workspace scope, we enforce strict boundaries. Your data scientists might have contributor access to the development workspace, allowing them to experiment freely. However, in the production workspace, they are granted only reader access, or perhaps no access at all. Only the automated CI/CD pipeline using its secure service principal is authorized to push a model into the production workspace. This diagram maps out our multi-workspace IAM strategy. Notice the three distinct subgraphs representing our dev, staging, and prod workspaces. In the dev box, humans are data scientists have contributor rights. But look at production on the right. Humans have zero standing access. Only the CI/CD pipeline, representing our automated service principal, holds contributor rights to deploy the final model into production. This structural separation is the pinnacle of a secure MLOps deployment. Let's apply everything we have learned to a real-world use case. Imagine you are an ML engineer at Prosware, a healthcare startup. Your team has developed a highly sensitive diabetes classification model using patient medical data. The business needs to scale this rapidly, but security and patient privacy are paramount. The challenge is to let data scientists experiment freely without risking production data or stability. The solution starts with creating isolated environments, a development workspace and a production workspace. Using Azure RBC, you configure identity and access management so that the data science team holds contributor rights exclusively in the dev workspace. They can train models and tweak parameters all day long, but they are physically and logically blocked from making any changes to the production workspace. This perfectly satisfies the zero trust requirement of least privilege. Here is the visual representation of Prosware's access model. The data science team on the top left has a solid line granting them contributor access to the dev ML workspace. However, notice the dotted red line leading to the prod ML workspace. They are explicitly blocked from accessing it directly. The only way a model moves from dev to prod is through a validated, automated registry process. This guarantees that no human can bypass testing and push unverified code to your live healthcare application. To complete our prosware use case, we must automate the deployment while maintaining our ironclad security posture. Since the data scientists cannot deploy to production, we implement a CI/CD pipeline using GitHub Actions. We generate a service principal specifically for this pipeline and lock its credentials away in GitHub secrets. We then assign the service principal contributor rights to the production ML workspace. Now, when the dev team finishes their work, the pipeline automatically and securely promotes the model. Finally, to ensure the model can access the sensitive healthcare data it needs for inference, we assign a managed identity to the production compute clusters. By granting this managed identity read-only access via RBC to the storage account, the compute fetches data without ever handling a password. The result, a fully automated, zero-trust compliant MLOps pipeline that protects patient data and scales effortlessly. Let's review the final sequence. The dev team merges their approved code, triggering the GitHub CI/CD pipeline. The pipeline, acting as our secure service principal, authenticates and deploys the model into the prod ML workspace. Once running, the prod workspace uses its keyless managed identity to request the necessary patient data from Azure Storage. The storage validates the identity via RBC, returns the data securely, and the pipeline completes. We have successfully secured our machine learning lifecycle from end to end.